Okay, so good afternoon, everyone. Um, so today we are starting a very fascinating topic called duality, also known as linear programming duality, because duality appears in many different contexts and areas in mathematics. Okay, so let's recall this example from the two-phase simplex method that we did earlier. Okay, so we had to maximize this objective function. It's basically a LP in standard equality form. And in the two-phase method, of course, we wrote down the auxiliary LP and we solved it. We found a optimal value of 0. So then we came back to the original LP and we solved the original LP. Also, we had multiplied the first constraint by -1 in order to do the auxiliary LP stuff. But anyways, the solutions we found for in the phase 2 are these two phase solutions, 201 transpose and 047 transpose. Okay, and you can check that both of these are indeed feasible solutions. We found them by simplex, so no surprise there. And their values are 6 and 10. And we concluded, let me just go back to the two-phase simplex page to show you the dictionary. So, right, so let's see. Okay. So we found 047 and the dictionary looked like this, right? So we concluded that this is an optimal solution. Okay. But let's suppose we don't want to go through the whole simplex method and we want to somehow just convince someone that 047 is indeed an optimal solution. Okay. So this is related to the certificate of optimality, but we are doing it in duality because it is extremely closely tied with duality. Okay. So the question is, how do we convince someone that 047 is indeed an optimal solution? Okay. Well, what is the value of 047? The value is 10. So this is equivalent to convincing someone that 10 is an upper bound on the optimal value, or it is the upper bound on the value of any feasible solution. Okay. So equivalently, how do we convince? Let me just say in short, how do we prove that 10 is an upper bound on the value of any feasible solution, right? Do you all agree that these are equivalent questions? So I want to ask a slightly more general question. So let's put it more generally. Rather than focusing on 10, I just want to ask, how do we establish upper bounds on the value of any feasible solution? Of course, we are talking about upper bounds because we have a maximization LP. So more generally, how do we establish upper bounds on the value of any feasible solution? Right? And we are talking about upper bounds since this is a maximization problem. Okay, whatever we are going to do is actually applicable to any kind of LP, right? But today we are focusing on this particular LP, which is in standard equality form. Okay, but the techniques that we are going to come up with, the arguments, they can be modified appropriately to apply to any linear program, okay, no matter what form it is in. We'll get to that later. Okay, so today let's just focus on this LP and see how we can find upper bounds. So the plan is as follows. The plan, as we have been doing for the last couple of lectures, is to take some linear combination of the constraints and see if we can use that particular linear combination in some nice way to get an upper bound. Okay, so it will become clear as we proceed. We will consider a few special, we will figure out later what is so special about them, linear combinations of the constraints. Okay, so I would like to write down the constraints here. So this is going to be constraint 1 and constraint 2, and we have the non-negativity, but we are going to take linear combinations of these two constraints. Okay, so let me just write them down. -1, -2, 1, -1. Is that right? Yeah. And the next one is 1, -1, 1, 3. So 1, -1, 1, 3. Okay. So this is going to be our constraint 1 and constraint 2. All right. So let's proceed. So the first combination I want to consider is -2 times the first constraint plus 5 times the second constraint. Okay. I'm using this asterisk because we also have lots of x's floating around. Okay, so what do we get if you multiply the first constraint by -2 and the second one by 5? Okay, let's see. So this becomes a 2x1 plus 5x1, that will be 7x1. This becomes a 4x2 minus 5x2, which will be minus x2. And this becomes minus 2x3 plus 5x3. That will be 3x3. Okay. And what is that equal to? That is equal to -2 times -1 is 2, 5 times 3 is 15, so we get 17. Let me know if I make any mistakes.
Sir, how do you get -2 and 5 then?
Yeah, we'll come to that later. So right now, these are just special linear combinations, and we will see why. We will see whether these particular numbers I've chosen work, and if they do work, why do they work? Okay. So right now it's magical, but hopefully we will reveal the magic soon. Does that answer your question?
Yes, sir, I get that.
Okay. Okay, so this is our constraint number 3. So we got this by taking a linear combination of the first two constraints, right? And therefore, every feasible solution must satisfy this constraint. Right? So every feasible solution, x bar, satisfies constraint number 3, which is the same as saying I can rearrange things and write it in a way that I like. 17 minus 7x1 bar plus x2 bar minus 3x3 bar is equal to 0. This holds for every feasible solution, right? Okay. So what is quite useful in mathematics is adding a 0. Sometimes adding a 0 gives quite nice results. So in particular, for any feasible solution, the objective value C transpose X bar, notice that we just have C transpose X bar, we don't have any constant here. Okay, so the objective value of our feasible solution, what is it? It is 2x1 minus x2 plus 2x3. So it is 2x1 bar minus x2 bar plus 2x3 bar, right? And I can always add a 0 to this. So that's what I will do. So I can add the left hand side here. 17 minus 7x1 bar plus x2 bar minus 3x3 bar. Okay. Okay, so what is this? Well, let's rearrange things to make it convenient. So let me just use some space so that we can optimize a bit. So let's say this is 17. And what do we get? Minus 7x1 bar plus 2x1 bar. So that's minus 5x1 bar. Minus x2 bar plus x2 bar, that cancels out. 2x3 bar minus 3x3 bar is minus x3 bar. Okay, and let me write it in a slightly different form, which will be convenient later. So it's 17 minus 5, 0, and 1 times x bar. Right? So what can you say at this point? At this point, what can you conclude about the optimal value of the feasible solution?
It should be 17.
It should be 17, or you mean something slightly weaker?
So it has to be 17 optimal solution, because anything if we put as x, it will drag down the value.
Right, but notice that by Simplex, the one we found was 047 and its value is 10. So we actually found an optimal value of 10. So are you sure you mean it should be exactly 17?
Oh no, 17 is like a big upper bound.
Right, 17 is an upper bound, right? We can't say it should be 17. That would depend on the feasible solutions, right? But what we do know is that all feasible solutions are non-negative. And so if you multiply a non-negative vector by another non-negative vector, we will get something non-negative. And so we are subtracting something non-negative from 17, and that is at most 17. Right? Is that what you mean?
Yes, sir. But this is a bit confusing. Why is it not 70? So this is a bit confusing. So we are subtracting something still.
Yeah.
Why?
Right.
Actually, that x bar could have been 0 because the non-basis variables like were allowed to be 0 there.
Okay.
Right. So in any feasible solution, it is possible that both x1 bar and x3 bar may not be 0. Right. So in particular, if you can find a feasible solution in which x1 bar and x3 bar are both 0, right, then you would actually get a feasible solution with 17 as the value. But we don't know how to prove that, right? In fact, based on our simplex, we actually know that 17 is not the value, it is 10. The 10 is the optimal. So at this point, the arithmetic we have done, it's very straightforward arithmetic. We can only conclude that the upper bound is at most 17. Right? Okay. But that is answering the question I wanted to ask, right? How do we establish upper bound? So we will get to the upper bound of 10. Right? So I deliberately chose a vector which does not immediately give you the upper bound of 10. So maybe if we choose a better vector, then we might get 10 instead of 17. Okay. Again, we will have to discuss what are the qualities, what are the special properties of these vectors, but we'll come to that later. Okay. So now I want to consider a second vector. So consider -1 times the first constraint and 3 times the second constraint. I want to point out a coincidence that I couldn't avoid because I'd already prepared my example. So -1 and 3 are also the values on the right hand side here. That is a total coincidence. Okay, there is no relation there. So it just happens to be a coincidence that I'm choosing this vector. Okay. So let's look at this combination. Okay. So what do we get? We get a new constraint. Let's call it number 4. And what is it going to be? -1 times the first plus 3 times the second. So it's going to be x1 plus 3x1 is 4x1. 2x2 minus 3x2 is minus x2. And minus x3 plus 3x3 is 2x3. And 1 plus 9 is 10. Okay. So every feasible solution satisfies this constraint. So I'm going to play the same game now. It's going to be slightly repetitive, but this will be the only two combinations we will consider, and then we will generalize our observations. Every feasible solution x bar satisfies constraint number 4, that is 10 minus 4x1 bar plus x2 bar minus 2x3 bar is equal to 0. Right? So the value of the objective function C transpose x bar, which we know is 2x1 bar minus x2 bar plus 2x3 bar. I can add 0 to it, why not? So that's what I will do. Right? And what is this equal to? This is 10 2 minus 4 minus 2 minus x2 bar plus x2 bar cancels out, 2x3 bar minus 2x3 bar cancels out. So I get exactly this, and I'm going to rewrite this in the following way: 2 0 0 x bar. Right? And as in the previous case, this is non-negative, this is non-negative, and therefore this is at most 10. So now we actually proved an upper bound of 10 on the value of any feasible solution. Right? Any questions or concerns? So at this point, we know that the solution found by Simplex 047 with value 10 was indeed an optimal solution. Right? No coincidence. I mean, no surprises there in some sense. We were expecting to eventually get there. Right? But what is so special about these particular vectors? Well, what is so special about these particular multipliers, -2 5 and -1 3, that was actually able to give us upper bounds, right? Can we just choose any two multipliers and will this work? So let's try to. So the question is, what is so special about them? Of course, the second one is even more special than the first one because it actually gave us the upper bound of 10 that we wanted, right? But even the first combination gave us some upper bound. It was not completely pointless. Okay. All right, so let us generalize what we have done. So in particular, why are these linear combinations able to give us upper bounds? Okay. So how did we get constraints number 3 and 4? We got them by multiplying the first constraint by some number y1 and the second constraint by another number y2, and then we added them, right? So what we did is we took two real numbers, y1 and y2, and we considered y1 times the first constraint plus y2 times the second constraint, right? And we noticed that any feasible solution satisfies this, right? In the first case, we chose -2 and 5. In the second case, we chose -1 and 3. Now, what does this, I mean, can we do all of this using vectors instead of specific multipliers, right? So can we generalize everything using vectors and matrices? So this is the same as saying that if x bar is any feasible solution, right? So what does that mean? That in particular means that ax bar is equal to b, right? And that would mean that I can multiply both sides by a row vector on the left, which is as good as taking a linear combination of the constraints. So y transpose ax bar is equal to y transpose b, right? Where y transpose is going to be our y1, y2, right? The multipliers we chose. And in particular, this means that y transpose b minus y transpose ax bar is equal to 0. This is exactly the 0 that we added to our objective value in order to get our upper bounds. Okay, notice that what we are adding here is exactly y transpose b minus y transpose ax bar, where y is -1, 3, the vector -1, 3. Okay, so in particular, the objective value of this feasible solution is, I can add 0 to it, right? And this is exactly equal to y transpose b plus, let me just go slowly. So C transpose X bar minus Y transpose A X bar. Notice that Y transpose B here is exactly what we got these numbers from, 10 and 17. Those were our Y transpose B's. And everything else was the rest. and this is y transpose B. And the way we wrote it earlier is we put a y transpose B minus the multiplication of two vectors, right? So let me take out a minus sign here, and that is going to be y transpose A minus C transpose times x bar. Okay, so just to go back to our example, y transpose B is this guy 10, y transpose this vector here 2 0 0 is simply y transpose A minus C transpose, and you have an x bar over here, right? And what we did is we concluded in both our previous examples that this was less than equal to y transpose B. Okay, so how were we able to conclude that? We concluded that this is less than equal to y transpose B. So my question is, under what why were we able to put this inequality? Right? I mean, if you look at this form here, it's not immediately clear that you can put this inequality, but we did. So what was so special about our vectors y that we were able to put this inequality? Anyone?
Y transpose A minus C transpose should be greater than or equal to 0.
Exactly. The fact that this vector here was non-negative in all our examples in the vectors y we chose, that is exactly why we were able to put less than equal to over here, because you're multiplying two non-negative vectors. So definitely the scalar you get out of that is going to be non-negative. And so you're subtracting something non-negative, therefore you can put that inequality. Right? So notice that in the vectors we chose, the vectors y transpose, we chose y transpose A minus C transpose was always a non-negative vector. So if this is true, so in particular what I'm trying to say is that if this is non-negative, then you can get a good upper bound. You can get some upper bound. It may not be a good upper bound, but you will get some upper bound, which will be non-trivial, right? So if you're looking for an upper bound of 10, well, you may get 1,000, I don't know. But to begin with, we did not even know that there was some upper bound, right? So whenever you have a vector y transpose that satisfies this condition, the corresponding y transpose B will be your upper bound. Right? So the observation that we have made, and we have essentially proved it at this point, right? You just need to go back and write it down as a proper proof. My intent was to show you the thought process rather than writing down a formal proof, which you should be able to do on your own going through these notes. Okay? So the point is, if y transpose is any vector y1, y2, for our example, that satisfies y transpose A minus C transpose being a non-negative vector, then the value of the objective function is going to be upper bounded by y transpose b, which is exactly the 17 and the 10 that we got. Okay. So any such y bar gives an upper bound on the value of any optimal solution. Let me actually remove y1, y2 because this is applicable to any number of constraints. Okay, so it is in the appropriate dimensions. Okay, so if you have any vector that satisfies this condition for a linear program in standard equality form, as we started in our example, then your objective value C transpose X bar will be upper bounded by Y transpose B, right? So this is true for any LP that looks like maximize C transpose X subject to AX equals B and X at least 0. Okay. Let's rewrite this. Let's write down this in a different way. So this is saying Y transpose A is at least C transpose. And now I can take the transpose on both sides and I can say A transpose Y is at least C. Same as A transpose Y is at least C. Okay, I've not done anything fancy. Okay. So any vector Y that satisfies A transpose Y is at least C will give you an upper bound which will be equal to Y transpose B. And now I want to ask you a question. Which such vector would give you the best upper bound? Supposing you want to find a Y. I mean, I'm not asking the algorithmic question. I'm asking the more sort of philosophical question, if I may, right? So you are trying to find a vector Y which satisfies A transpose Y is at least C. And you want this vector Y to give you the best possible upper bound. So what should you be doing? Is there something you should be optimizing? So just to be
It's like
clear,
solving the it's like optimizing Y transpose B with the constraint that A transpose Y is greater than or equal to C.
what do you mean by optimizing here?
Uh,
Here you want to minimize, I think.
Minimize, right? So you mean minimize. You want to find
Yes.
a Y that satisfies these constraints and minimizes Y transpose B, right? And Y transpose B, I can write as B transpose Y. Okay. So you want to minimize B transpose Y subject to, oh, is that another LP? Do we have another LP here? Right? So that's exactly what's going on here. We are trying to minimize B transpose Y subject to A transpose Y being at least C. So that is our constraint. Y is a free variable. Remember, we had no constraints on Y because we can multiply the equations by any number we like because they are equations. If they were less than equal to or greater than equal to, then we would have to be careful. We might not be able to multiply by any variable, or if we multiply, then we might have to flip the sign, right? But because our original LP had just equations, our y's did not have any constraints. We can multiply both sides by any number we like. Right? So what we are really trying to do, we are trying to find a vector y that satisfies these constraints. Well, the second one is not really a constraint. I'm just writing it explicitly to make it clear that it's a free variable. And we want to minimize V transpose Y. So this is basically another LP. And what we did is we considered two feasible solutions to this LP. The first one was -2, 5, and the second one was -1, 3. And when we put -1, 3, we actually got the upper bound of 10. This LP is called the dual LP. Okay, so if your original LP, which is called the primal LP, so if this is your primal LP, then for every linear program, there is a dual LP. And in this particular case, when your primal LP looks like this, your dual LP is exactly what we found. And if you have any feasible solution for the primal LP, X bar, and you have any feasible solution to the dual LP, Y bar, then C transpose X bar is less than equal to B transpose Y bar. The value of the primal LP feasible solution is always less than equal to the dual LP feasible solution. And basically, we proved all of this here. So looking at these notes, you should be able to write down a complete proof of this theorem that I'm about to write down in full detail. Okay, so I'll put down a theorem that we essentially proved here, but I want you to write down the entire proof going through these notes. It should be fairly straightforward. So I'm going to call this theorem 3.9 GKT. So consider the following pair of LPs. So the first LP is maximize C transpose X subject to AX equals B and X is non-negative. The form of this LP basically dictates the form of the dual LP. We will actually see how to convert, how to write for any linear program in whatever form it is, how to write the dual linear program. Largely, I mean, one can go through the whole process and figure it out themselves, but there's also a nice way to just memorize it once you are comfortable with deriving it yourself, right? So I'll also give you some notes that will make it easy to memorize how to find out the dual LP. But the whole point is that if you forget it, you should be able to derive it yourself by going through the arguments that we did in this lecture. Okay, so, and I'll give you some practice problems as well to become comfortable with this. So for this LP P, the dual LP looks like exactly what we wrote down. And generally, I write down the free variables explicitly. But you don't need to write it. You can just omit y free. And so the claim is that let X bar be a feasible solution for the primal LP and Y bar a feasible solution for the dual LP. Then C transpose X bar is less than equal to B transpose Y bar. Right? And what can you say if you find an x bar and a y bar that satisfy this with equality. Supposing you can find an x bar and a y bar that satisfy this with equality. So C transpose x bar is equal to B transpose y bar. Then what can you say about x bar and y bar? This is similar to one of your assignment problems. I hope you can see the similarity. Right. So furthermore, I'm waiting for an answer. If equality holds in this case, then I would like someone to fill in the blank here.
B transpose y bar will be optimal.
Sorry, B transpose y bar will be what?
Wait. Sorry.
If we have equality, I think C transpose X will be the maximum and B transpose Y will be the minimum. So I think X and Y, X will be the optimal for C transpose and Y will be optimal for the B transpose.
Right. X bar is an optimal solution for the primal LP and Y bar is an optimal solution for the dual LP. Right. So whenever equality holds.
Now, there's something that's kind of striking here. So is this very similar to one of the questions in assignment 1 that was vertex cover and independent sets? Are they also primal and dual forms of each other?
No, they are not primal and dual forms.
Okay.
Well, it is also similar to another question about matchings and vertex covers. Right. So,
okay.
What I asked you in one of the problems was to show that the size of any matching is upper bounded by the size of any vertex cover. And I had asked you specifically, what can you conclude if for some matching and vertex cover, the cardinalities are equal?
Yes, sir. So that I remember. But
right. So
I think
those
there
are
was
actually
one...
primal and dual.
Oh, okay.
Yeah.
Because I think there was one related to vertex cover and independent sets.
Yes,
so...
that is also true, but that is not related to primal dual stuff. That is just theoretical somewhat.
Okay, because there also maximization of one will do minimization of the other.
That's right. But they are not primal dual forms. In fact, the primal dual holds for, if you write down the primal and duals, you will see that it's actually matching is related to vertex covers.
Okay, I should see this.
Yeah.
This is very strikingly similar.
Yes, I agree. I understand your point. Right. So if equality holds, then we know that X bar is an optimal solution for the primal LP and Y bar is an optimal solution for the dual LP. Okay. So do it yourself exercise is to write down a complete proof using these notes. Okay, so the proof is in here. I did not want to just give you a theorem and write down a proof. I wanted to go through the whole discussion. So I think you should be able to figure out the proof yourself by going through these notes. Okay, essentially it's the stuff that we did here. Okay. All right. So this is worth writing down. So there is a point I want to make here. Actually, the theorem 3.9 in GKT is not exactly what I have written here. They consider a different form of LP. So this kind of a theorem is called a weak duality theorem. And you can write a weak duality theorem for any special form of a primal linear program. And according to that, you will write down the dual linear program, right? So this kind of theorem is called weak duality theorem. Why is it called weak duality theorem? You see, we are not saying that there will always be a feasible solution x bar and a feasible solution y bar for which equality will hold. We are not claiming that in this theorem, right? We are just saying that if x bar is any feasible solution and y bar is any feasible solution for the dual, then C transpose x bar is upper bounded by B transpose y bar, right? I'll actually like to illustrate this by drawing. So think of, in our example, the primal LP is a maximization problem, and the dual LP is a minimization problem. I want to draw the number line quickly here. So what are the solutions we found by Simplex? We found 6 value and we found 10, and then we found upper bounds of 10 and 17. So one way to think about it is consider the number line. Okay, so the primal LP is trying to maximize a certain objective function. The dual LP is trying to minimize a certain objective function. So what this theorem is saying is that, right, so 0 is here and -1 is somewhere here and 1 is here, right? So you get the idea. So what this theorem is saying is that for any feasible solution of the primal LP, you look at its value, it will be some C transpose x bar, and you look at any feasible solution of the dual LP, it will be some B transpose y bar. So the theorem is saying that it will always be the case that C transpose x bar is less than equal to B transpose y bar, right? So in our example, we actually found 6, 10, and 17, right? So let me erase this. So let's say 6 is here, 10 is here, and 17 is here, right? In our example, we found 2 feasible solutions, x bar, x prime, and x double prime. And we also found a y prime and a y double prime. And it just so happened that for the specific x double prime and y double prime, the values happen to be equal. That is when we know that both the solutions are optimal. But the theorem is not saying that there will always be an x bar and a y bar for which equality will hold, right? So this is something I want you to note here. And that is what strong duality says. So we will see strong duality later, but I can already give you the idea that strong duality theorem says that there will always be an x bar and a y bar for which C transpose x bar is equal to B transpose y bar, right? So I hope I can convey the difference between weak duality and strong duality to everyone. Right? So the theorem does not say that there exists an x bar and a y bar such that C transpose x bar is equal to B transpose y bar, right? That is why we have a if over here. We don't know that such x bar and y bar will always exist. The fact that they always exist is called the strong duality theorem. Okay? So strong duality says they exist. Okay? So what we have proved today is simply the weak duality theorem for this special form of primal linear program, which dictates what the dual linear program looks like. Okay? The theorem 3.9 in the text one of the texts we are following is actually different. Instead of this being a maximization problem, they consider this being a minimization problem. So the primal could also be the minimization problem, in which case the dual will be the maximization problem. Also, you might be wondering, is the dual of the dual back originally the original primal problem? The answer is yes. The dual of the dual takes you back to the primal problem, right? Which would make sense. Okay. So I would like you to try it yourself. Prove a weak duality theorem for the following linear program. So the primal is the same as before, but I have changed it to a minimization problem. Right? So now instead of finding upper bounds, your goal is to find lower bounds. And that's the way you want to think about when you try to solve this problem. Right? So you're trying to establish lower bounds. And I want you to figure out the dual yourself. Okay. And this is actually the theorem 3.7, sorry, not 3.7, 3.9 in one of the texts we are following, right? Notice that this is also the form of the theorem. This is also the form of the linear program for our matching problem. We are trying to minimize the cost of the matching, perfect matching, subject to some equality constraints and non-negativity constraints. Right? Notice that this is the same form as the LP relaxation of the minimum cost perfect matching problem that we wrote in our first module. Right? So that's the same form as this linear program. Okay. So please check. All right. And this kind of problem, this kind of try it yourself problem, or the same one, might appear on your assignments. So I hope that you all will go through the arguments we did today and try to make similar arguments for this different kind of linear program. Okay. So the point is that for any linear program, there is a dual, right? And the dual of the dual brings you back to the primal. Right? So I'll make a note of this. Every LP has a dual LP, and dual of a given linear program is back the original linear program. Okay. And we will see in later lectures, I'll also give you some type notes that basically will help you memorize how to write the dual of any linear program. But as I said, the important thing is that you know how to derive it yourself. Okay, so that's all for today. If there are any questions or concerns, I'm here for another 10 minutes.
So here you said that, can you just show that in the duality?
Yeah.
Strong duality, if we have only, then we can have C transpose X is B transpose Y. So
Right.
is there a condition to know if a strong duality holds for a given LP?
It always holds. So strong duality theorem says that you can always find an X bar and a Y bar such that C transpose X bar is equal to B transpose Y.
Yes,
Right?
sir. So
We
if we
haven't-
have strong duality, then why do we need weak duality? So if we know that we'll always have a solution, why is
it's
weak
just,
duality?
okay, good point. So there are a few answers to that. So the first answer is weak duality we already proved today. Do you agree? We essentially
Yes.
proved weak duality for the particular form of linear program that we were considering, right?
Okay.
So proving weak duality is significantly easier. Our
Okay.
proof of strong duality is actually going to depend on the simplex method. So we are going to assume that the simplex method terminates, which we did not prove, and we are going to use that to show that strong duality holds. Right? Weak duality does not require any fancy stuff. It does not even require the simplex method. To be fair,
Okay.
you can also prove strong duality without using the simplex method. But in this offering
Okay.
of the course, we will not be covering that. In this offering, I'm going to focus on the using the simplex method, termination, and then proving it. Right?
Okay.
The second answer is that using weak duality. So, in fact, when we go to primal dual algorithms, what we will really be using is this statement. So we will actually design combinatorial optimization algorithms where we find an X bar and a Y bar that satisfy this with equality. Right?
Okay.
So at that point, just using weak duality, we will be able to conclude that this we have found optimal solutions. So we don't need strong duality for some of the things. Of course, it is nice to know that strong duality exists for all linear programs, right?
Okay.
So it kind of provides a natural progression into the strongest theorem out there.
Okay.
Yeah.
I was just confused that when we have an equality and that equality gives us such a big point that we have a maximization at one and minimization at the other, why do we even need
Right, right. No, that is a very fair point. So there are a few different reasons why we still talk about weak duality.
Okay, sir. I will just look that up.
Okay.
And sir, regarding the assignment in one of the questions, I think it was 2D. There was, I think 2D or 2E. There was something that we were asked to construct the graph as well,
Okay.
showing G, X bar, F, H, and all.
Yes.
I think
yes,
it
I
was
remember
related.
that.
So,
Yeah,
so we can again put some text images showing my graph and how it progressed.
Sure. So long as all the details are clear, it should be fine.
Okay, sir. I'll do.
Yeah. Okay. Any other questions or concerns? Okay, so I'll stop recording now.